Hello everyone, I am Kyoung-Hee Kim, a professor of architecture. We will discuss eco-properties of sustainable building materials in this session. We reference key texts such as Materials and the Environment by Michael F. Ashby and Turning Point in Timber Construction by Ulrich Daniel. These works provide foundational knowledge on eco-informed material choices. We discussed this chart in the previous videos. Here we have an overview of a building's major systems and components. We divide the building systems into 5 categories: the site system, the structure, the enclosure, the services, and the interior system. For example, the site category covers elements around the building such as pathways, landscaping, outdoor furniture, and so on. The structure is the building skeleton made of steel, concrete, or timber frame. The enclosure consists of the walls, windows, and roof that protect the interior. Services include systems like HVAC, heating, cooling, and ventilation, electrical systems, IT networks, plumbing, life safety, transportation, and other utilities. Finally, interior systems consist of finishes, appliances, and furniture. Together, these systems are integrated to create the entire building and define its performance and aesthetics. Now we shift to a life cycle perspective. This diagram, based on the EN 15978 standard, shows the inputs and outputs over a building's entire life cycle. While embodied energy concerns the cradle-to-gate system boundary, it is important to understand the inputs of energy, water, and raw materials and pollution outputs for the entire life cycle of building systems. On the input side are the raw materials, energy, and water that go into fabricating, manufacturing, and operating a building system. Moreover, we strive to recover building components or whole assemblies for reuse, as well as recycle materials at the end of their service life and even regenerate the raw materials. We can significantly reduce the environmental footprint at every stage of the life cycle. Next, let's look at the embodied energy of materials, the total energy required to produce 1 kilogram of each material. In this chart, each color-coded bar represents a material family. Construction metals on the left tend to have relatively high embodied energy per kilogram. For example, producing aluminum is energy intensive on the order of hundreds of megajoules per kilogram, while steel, though lower, still requires tens of megajoules per kilogram. The polymers group also requires a lot of energy to produce, often around 100 megajoules for 1 kilogram. Ceramics and glasses, including concrete, brick, and glass, have much lower embodied energy per kilogram. For example, a kilogram of typical brick or concrete might take only a few megajoules of energy. Hybrid composites can vary widely. Some synthetic composites like carbon fiber have very high embodied energy, whereas wood-based composites are much lower embodied energy. The main takeaway is that different material classes carry very different energy costs and environmental footprints in their production, which is called eco-properties. Now let's compare the carbon footprint per kilogram of these material classes, the kilograms of CO2 released for each kg produced. This tends to follow the energy pattern. Metals are relatively high emitters, making a kilogram of steel might emit around 2 kilograms of CO2, and aluminum can be several times higher due to its huge electricity demand. Polymers also have a high carbon footprint. Polycarbonate, for example, has approximately 5 kilograms of CO2 per kilogram of material. In contrast, ceramic materials like concrete or brick have less than 1 kilogram of CO2 for 1 kilogram of material. Although concrete belongs to the lower emission category, the large volumes used for foundations and structural systems significantly increase the overall carbon footprint. Hybrid composites have footprints that combine those of their ingredients. For example, a fiberglass panel carries emissions from producing both the glass fibers and the resin. The takeaway is that per unit mass, materials like aluminum and plastics are very carbon intensive, whereas concrete is relatively low per kilogram material, though we use concrete in enormous amounts. Now we shift from per kilogram impacts to total global carbon emissions associated with each material category. This chart shows how much CO2 each group of materials is responsible for annually. Steel production in particular releases a very large amount of CO2 globally, followed by cement and concrete. Even though concrete's emissions per kilogram are low in the previous slide, we use so much of it that cement production is one of the biggest single sources of CO2 worldwide. Polymers, plastics, also add a significant share of emissions, though less than metals or concrete. Hybrids, composites, account for the smallest slice of the global total, simply because we produce relatively little of these materials. The key point is that to cut global emissions, we have to pay attention not just to the intensity per kilogram, but also to the sheer scale of material use like concrete and steel worldwide. In the previous LCA slide, we discussed that producing any material requires water input. Water usage is the amount of water required to produce 1 kilogram of material. This slide illustrates water usage measured in liters per kilogram of material. Metals tend to use a high volume of water in their production. Think of mining and refining metals or cooling in steel mills. Those processes can consume significant water per kilogram of metal, though often recycled on site. Polymers use water mainly for cooling and chemical processing and typically consume a high volume of water per kilogram. Ceramic materials like concrete, brick, and glass require water as well, for example, mixing concrete or cooling molten glass. But generally, their water use per kilogram is lower compared to the metal or polymer groups. Composite materials will have varied water footprints depending on how their constituents are made. This chart emphasizes that managing industrial water use is important, especially in regions where water resources are limited. Another key aspect when selecting materials is how much we reuse or recycle our materials. This slide shows the current recycled fraction in the supply for each category, basically, the percentage of recycled material input. Metals have the highest recycled content. We have well-established recycling for steel, aluminum, copper, etc. So a significant portion of metal production, often a few tens of percent, comes from recycled scrap. Polymer recycled fractions remain quite low. The ceramic group, such as brick and concrete, has a higher recycling rate than polymers, but it is still lower than the metals group. Hybrid composites are also challenging to recycle. Virtually none of these materials are recycled currently due to technical difficulties. So while we're doing well with metal recycling, there's a lot of room to improve the recycling of plastics, concrete, and especially composites. This chart shows the percentage cost increase for each material if we impose a $20 per ton CO2 tax. Materials with high emissions and low cost experience the largest jump. For example, metals like aluminum alloys might see their material cost increase by 10%, while steel would experience a moderate rise of 7%. Cement and concrete are very carbon intensive, yet cheap, so their price might increase by around 10% or more under that tax. Polymers are relatively expensive per kilogram, so a carbon tax would only add a small percentage to their price, maybe a couple of percent. High-cost composite materials would be affected the least, since they're produced in smaller volumes and are already expensive. The carbon fee remains a tiny fraction of their cost. In short, a carbon tax would shrink the cost advantage of carbon-heavy materials like metals and concrete and encourage the use of lower carbon options. Summary highlights: 1. Material production impacts vary widely. Different material classes have very different energy demands and carbon footprints during production. 2. Scale matters as much as efficiency. Reducing global emissions will require concrete and steel industries to improve their manufacturing efficiency and minimize material consumption. 3. Water usage is an important metric. Managing industrial water use is important, especially in regions where water resources are limited. 4. Recycling performance is low across materials. The recycling of plastics, concrete, and composites still has much room for improvement. 5. Carbon tax changes material economics. Carbon taxes would increase the cost of carbon-intensive materials like steel and concrete and encourage the use of lower carbon options. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in sustainable materials and eco-properties.